Hi, I welcome all of you in my channel and in this video in which I am going to discuss a latent scale design. The latent scale design is a statistical design of experimental technique in which we block our two Nissen's factors. Nissen's factors are those that affect our process, but we are not interested in their effect. So we have to block them by any statistical technique. A significant assumption of latent scale design is that the three factors that have been involved in the LTS latent scale design, they do not interact with each other. In the further videos, we will do the interaction of the factors by using a factorial design technique. If the assumption that is violated, that if the factors are interacted with each other, the results produced by the latent scale design will not be valid. In order to study the application of latent scale design, I will discuss a problem and I will solve this problem from the hypothesis formulation till its conclusion, and the calculation will be manual as well. Suppose that an experimenter is studying the effect of 5 different formulations of a rocket propellant used in the air-crew escape system on the observed burning rate. So the observed burning rate, this will be my response variable, and the effect of 5 different formulations. So the formulation become my factor of interest. This will be our main factor, and I will perform the 5 treatments. Okay, and then we will move forward. Each formulation is mixed from a batch of raw material that is only large enough to make the 5 formulations to be tested. One thing that is most important in this, that we have the design for the latent scale, it should be balanced. I mean that if I have 5 different formulations, so then there will be 5 different levels of both Nissen's factor. Means the design should be 5 cross 5, or it should be 4 cross 4, the 4 levels of the treatment and the 4 levels of the Nissen's factors. And then furthermore, the formulations are prepared by several operators, so there may be substantial differences in their skills and experience of the operator. Thus, it would seem that there are 2 Nissen's factors to be averaged out in the design, and those Nissen's factors are batches of raw material and operators, and I will take 5 levels of each of the Nissen's factor. The appropriate design for this problem consists of testing each formulation exactly once in each batch of raw material, and for each formulation to be prepared exactly once by each of the 5 operators. Let me show you this last statement, this last paragraph in the data. So this is my data, and after this I will show you the hypothesis. These 1, 2, 3, 4, 5, these were my batches of raw material. My Nissen's factor number 1, you can say these operator, it are 1, 2, 3, 4, 5. This is, you can say, Nissen's factor 2. And the treatments in the latent scale design, they have been represented by A, B. These are the latent alphabets A, B, C, D, and E. So please make sure while you're solving the question that each of the row, it doesn't contain any repetition of the formulations or alphabet. I mean that if you talk about row number 1, so you can see it contains A, B, C, D, and E. It doesn't contain any repetition of the alphabet. Likewise, if we talk about this first column, so A, B, C, D, E, no repetition. Likewise, if you select any of the row, let's talk about column number 4. So A, B, C, D, and E. Again, if you talk about row number 5, so A, B. So this is a 5 cross 5 design that contains equal number of rows and columns. We will formulate our hypothesis. As we have 3 factors, so there will be 3 hypotheses represented by H1, H2, and H3. So first hypothesis is related to the treatments or factor of interest. So we will say that test for hypothesis formulation does not affect the burning rate. Burning rate is my response, and the formulation level is my factor of interest. The second hypothesis based upon my Nissen's factor number 1. Test for hypothesis that the batches of raw material not affects the experimental output, or in place of experimental output you can write burning rate. Third hypothesis, test for hypothesis that the operators do not affect the experimental output or burning rate. Let's discuss the mathematical model. In this mathematical model, each observation that is represented by yijk is equal to mu, that is the overall mean. Alpha I is the effect of the ith row. We have 5 different rows there. Then tau j is the effect of treatments. We have 5 different treatment levels represented by A, B, C, D, E. Bk is the effect of blocks. So we have 5 columns that represents the our operator factor, and epsilon I, jk. This is basically the residual term. Again, the same assumption that our residuals will be NID, normally distributed, normally and independently distributed. So we can satisfy this assumption of normal and independent distributed by using the graph, and this graph you can generate in the Minitab software. Further, this 0 means that the mean of all of the residuals, they should be equal to 0, and 1 is the variance of those residuals. And then based upon all those residuals, we will calculate our random error term, that we call it MSE, mean square of the error. Sometimes we call it the pooled standard deviation. Also, the variance of overall model. The sum of square total in this case is equal to sum of square of the rows, nicest factor number 1, sum of square of the columns, nicest factor number 2 sum of squares, and sum of square of the treatment that have been represented by the alphabets, and then sum of square of the error. These are associated with them are the degrees of freedom. You can see that p minus 1 are the same degree of freedom for rows, columns, and treatment. It is because we have equal number of rows, column, and treatments. This is the basically this is the condition of latent scale design, that number of column, and number of treatment should be same, so the degree of freedom are also equal to each other. The SST degree of freedom will be calculated by using p square. So in this problem we have 5, p is equal to 5. I mean, there are 5 different levels. So we have total 25 observations, and then p square 5 square 25 minus 124 degree of freedom. And for the sum of square of the error, we can calculate the degree of freedom by this formula, p minus 2 multiplied by p minus 1. How we will use them? So after calculating the sum of square, we will divide them to their degree of freedom, and we get the ratio. This ratio is called mean square or MS. And then the ratio of mean square of the treatment to the mean square of the error is the F naught or F statistic value or F calculated value. We will compare this over F statistic or F calculated value with some F tabulated or F critical value. The F critical value can be obtained by using the degree of freedom p minus 1 for the numerator and p minus 2 multiply p minus 1. This is the degree of freedom for the error term. So this term will be my F critical term, and we have some value associated with it. It is called alpha, and in most of the cases we take alpha is equal to 0.05. If you have any question, you can ask me in the comment section. Thanks for watching the video. Kindly hit the like button, subscribe to my channel. You can also contact me on my WhatsApp number as well as on the email. Bye.